Hi everyone. So today's lesson is on inverses, specifically inverses of functions. And just so you know, today we're going to kind of talk about what an inverse function is and how to find it. And then tomorrow we continue with the topic of inverse functions and talk about some of their special properties. So what do I mean when I'm talking about an inverse? Well, we've talked about some inverses before, specifically inverse operations. Inverse operations are operations that undo each other, and that's kind of pointed out here in this part of the definition. So, for example, addition and subtraction are inverses of each other because they cancel each other out. They undo each other, or squaring and square rooting, things like that. But when we're talking functions, essentially what happens when you're finding the inverse of a function, remember a function is all about pairing up like an x and a y. So with an inverse, the x and the y reverse. The x becomes the y and the y becomes an x. Okay? And I think I was going to throw an example in here, but I think we'll just jump down to example 1 and start talking through that one. So we need to remind ourselves from way back in chapter 1, how do I know from looking at this set of ordered pairs, is this thing a function or not? And I'm really hoping you said yes it is, because if you look at all of your x values, we've got 3, 4, 6, and -1. None of those pair up more than once. So as an answer to this question, I would say yes. And just to make it more concise, the x values do not repeat. That's what you're always looking for. Okay, essentially what it is you don't want the x's to be partnered up with more than one number for y. Okay, and that's what would happen if the x value is repeated. Okay, domain and range. Domain is what are your possible x values, so we're really just listing our values of x, and if we're going to be good mathematicians, we're going to list those values of x in order, although that's something I don't usually get too picky about. So 3, 4, 6, and -1, I would list as -1, 3, that's supposed to be a 3, 4, and 6. That's my domain. That's all my possible values of x. For my range, it's all of your possible y values. Now you will notice with the y's, there is a repeat, right? 4 is matched up with 1, and -1 is matched up with 1. In terms of being a function, we don't really care if the y values repeat. It's only the x values that we worry about. But when we're listing the range, we don't have to list those repeats. Okay, so really we just want to say that we've got a 2, a 1, and a 0, so I'd list that as 0, 1, and 2. Okay, so that stuff is all review. That's stuff that we've done before. Now we're going to write out the inverse of this function, and this is really the new stuff today. This is really the goal for today is, can you do this? Ready? This is complicated here. To find the inverse, we're going to take all these coordinates and switch them around. 2, 3, 1, 4, 0, 6, and 1, -1. Okay, that's how you find an inverse, is you literally just switch x and y in every single coordinate. And by the way, because I see this notation is going to come up later on, the notation for an inverse of a function is if this up here was f, then we would call our inverse f with a little -1 up here. And that's not anything mathematical. That's not like an actual exponent or anything. It's just notation for inverse. Okay, so think about your domain and range now. Think about what just happened. All right, now I would say that my domain is, let's see, we've got 2, 1, 0, and 1. So I would say 0, 1, and 2. And for my range, I would say -1, 3, 4, and 6. Okay. And I'm kind of dodging some obvious observations here, specifically because I see that they're coming up in these next two questions. Okay, so I'm specifically kind of not addressing some of these things, but we're about to talk about them. So notice, what do you notice about the domain and range of f and its inverse? So what happens, with domain and range from here to here? Well, you probably noticed that even as you were writing them down, that really domain and range just switch. Okay, which should make sense. If you're switching the x and the y's, then the domain becomes the range and the range becomes the domain. And is this thing that we just came up with, is this now a function? Well, remember that repeat we had in the y's back here that we said we didn't really care about? Well, now that repeat shows up in the x's. Now I have 1 being matched up with 4 and 1 being matched up with -1. That's a problem, right? So I would say no, because 1 is paired twice, now that I've switched things around. But the important thing I want you to gather from this is that it doesn't matter that this thing was a function to begin with, all right? Just because it was a function to begin with doesn't mean that the inverse is necessarily a function. Or you could start with something that's not a function, and it could become a function when you find the inverse. So being a function or not is not held consistent from a function to its inverse, okay? It's something that you have to kind of evaluate separately. Okay, let's move on to example 2. And I do want to point out that this question right here, I believe I changed it from what's printed in your notes. So you probably have a question that says, like, write the equation. We are going to talk about writing the equation in a minute, but for right now, will you change that question so it says list 6 ordered pairs that are a part of f? And let's see, this is just the y equals x squared function. So I'm just going to throw some numbers in there for x. You know, my favorite is 0, 0. Well, 0 if I plug in for x, but 0 squared is just 0. If I put a 1 in there, 1 squared is just 1. Oh, let's throw in a 3. 3 squared is 9. Make sure I get some negative numbers in there. So I'll do -1, and when I square -1, I get +1. -2, and when I square that, I get +4. Oh, and let's see, we'll just keep going, and we'll do -3 squared is +9. And then I want to take those 6 points, and by the way, I could have picked anything I wanted. I was trying to pick points because I knew we were going to be graphing down here in a second. I picked points that were small enough to fit on here, but we could put anything we want in there for x, okay, and make up another point. So I'm going to graph these points. There we go, miracle of modern technology. I graphed the 6 points that we listed up above. Did I get all 6? Yeah, all 6 are on there. And so I could now take those and connect them, right, with the, let's see how I do here. But we were all smart enough to know what shape that was going to be, right? Y equals x squared is going to be a parabola, okay? So, and this is kind of the parent function for the parabola. This is the most basic one we can think of. All right, so then it says, is the inverse a function? So before I think about the inverse, let's take a look up here, all right? And find the inverse, just like we did in the previous example. So remember, the inverse is formed by just reversing all of these coordinates. So something sort of like that. Okay, I just took all my x's and y's and flipped them around just like we did before. Okay, and then I'm going to go ahead and graph this thing so I can get an idea of what the inverse would look like on the graph. Notice that 0, 0, and 1, 1 just happen to work out to be in the exact same spots. And then I've got 9, 3, 1, -1, 4, -2, and 9, -3. All right. And so when I go to graph this one, it turns out to be a sideways parabola. Okay. So my question down below, once again, was, is the inverse a function? The red one, is it a function? And we could answer that from the graph, or we could answer it from our ordered pairs up above. So I'm going to kind of leave both of those showing. Actually, I'll shrink it so we can see the question too. Based on the graph, do you remember something called the vertical line test? Okay. If we look at that red function, that thing fails the vertical line test, because if I draw a vertical line straight through really anywhere here, I hit the graph more than one time. Okay, so we could say that it fails the vertical line test as a justification. Okay, so I guess our answer is no up here. Or looking at the coordinates, we can see that we've got a couple of repeats in here, and probably if we had made up more coordinates we would have had even more repeats. But like, for example, 9 comma 3 and 9 comma negative 3, 1 comma 1 and 1 comma negative 1. We've got some x's that repeat, so we could justify it that way too, right? Or we could say the x's repeat. Either one would be an answer. So I want to come back and talk about the graphs of these functions a little bit more in just a minute, and something else we could have done to save us all the work of having to come up with either the ordered pairs up here, the ordered pairs up above, or drawing the graph. But before I do that, I want to answer this question down here. How do the two graphs appear to be related? Okay, what's the relationship between the two? And I know a lot of people are going to say, like, you know, oh, this graph turned, right? It rotated. It didn't technically rotate. I realize that on this one it kind of looks like that. But the relationship should actually be a reflection. And I'm going to show you where the reflection line is. Okay, came out a little bit shaky, but if I drew that diagonal line across my graph, corner to corner, and then folded right along that line, these two graphs would line up. If I have two inverse functions, they are always going to be a reflection over the line y equals x. Y equals x is that diagonal line that goes straight across. Okay? Because if you think about it, that line represents where your y and your x value are exactly equal to each other. And so you're always switching positions on either side of that line. Okay? And so let's answer this question real quick. How do the two graphs appear to be related? They are a reflection over the line y equals x. That's going to be an important relationship with inverse functions. And I actually don't think we write that down formally until tomorrow, but it's going to make sense in terms of what we're about to talk about with these graphs. So remember, I promised you a second ago that there was a quicker way to figure out the answer to this question, is the inverse a function, without actually figuring out what the inverse is. And that's something called the horizontal line test. Not the vertical line test, but the horizontal line test. So let me back you up a second. This purple graph, the purple parabola here, that one's a function, right? The vertical line test works everywhere on it. So we know that one's a function. But we also know that if I was going to find the inverse, this parabola is going to end up always getting kind of flipped on its side. And so if I were to draw a horizontal line through that parabola, if I was to draw a line like here, okay, and it hits the graph more than one time, that's a pretty solid indicator. In fact, it's a, surefire indicator that when I tip that parabola over the line y equals x, my new function is going to fail the vertical line test. Okay, so this line shows the vertical line test on the inverse. This line here shows the horizontal line test on the original graph. Okay, and so the horizontal line test is used on the original function to decide whether or not the inverse will be a function without actually having to draw the graph. And I mean, this one wasn't hard to graph, but there may be some other functions that it would be a little bit tougher to draw. Okay, so the horizontal line test you can use on an original function to determine whether or not the new function, when you find the inverse, will actually pass the vertical line test or not. Okay, so just in short, that's your definition of horizontal line test. I'll write it out real quick so you can make sure to have it in your notes, but probably one of those things that's easier to just see in action. So if you want to write something down formally for the horizontal line test, here you go. Horizontal line test is used on a function, really on the graph of a function, to determine whether or not its inverse is a function. Okay, so it doesn't determine whether or not the graph itself is a function, but whether or not the inverse will be a function. Okay, feel free to pause it if you need a second to keep writing. I'm going to keep moving. Okay, I need to throw one more example your way, and I realize you don't have this in your notes. That's okay, just try. And it is important that you write it down, though, because this is an important piece of inverses. It's going to come up on your homework tonight. And that is how to find the equation for an inverse if you're given an equation to start with. So let's suppose I give you the function f of x, which we all know is really the same thing as y equals, right? Maybe I'll even do this. F of x is y equals 2x minus 6, let's just say. Oops, where's my pen? 6. 2x minus 6. That's my original function. Now I want the inverse. And just like before, remember, inverses are all about switching x and y around. So that's exactly what I'm going to do. I'm going to say x equals 2y minus 6. And technically that's my inverse. But I need to get y back by itself in order for me to write my final answer. So I'm going to start by adding 6 to both sides, making this x plus 6 equals 2y. And then I'm going to divide by 2, and then over here everything gets divided by 2. Notice I didn't write the entire thing over 2, I did it separately. That's going to be important because there are some places, like right here, that things are going to simplify. So let's see, those cancel. I'm going to start with my y equals. Okay, so I'm just moving my y over to the other side. X over 2 would really be like 1/2 x, although if you left it as x over 2, that's okay. And then plus 6 over 2 is 3. And then this right here is the inverse of my original. Okay? And just to kind of drive this point home a little bit, I'm going to draw just a real rough sketch of these two things. So that original one, y equals 2x minus 6, let's see, I'll do that one in orange. That one would start down here at -6 and go, let's see, up 2 over 1, up 2 over 1. So it'd probably look, I don't know, something like this. Probably that slope needs to be a little steeper, but that'll work. Okay, 1/2 x plus 3 is going to start at +3, which I don't know is maybe there. It's going to go up 1 over 2, up 1 over 2, and this line's going to look something like this, which you may not think is, you know, real remarkable. There's not a whole lot of relationship there. But if you drew in that line, that diagonal line y equals x, you would see that these two lines should be reflections of each other over that red line down the center. Okay, again, that red line down the center is meant to represent y equals x. I did this whole thing without numbers, so kind of hard to see that, but that's the relationship between an inverse or a function and its inverse. Okay, and the way you find it is always just by switching x and y around and then resolving for y, digging the y back out and getting it by itself. Okay, we will continue with inverse functions tomorrow. Until then, you do have a homework assignment posted out of section 8.2.